Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at some topical past paper questions on the topic of forces, density, and pressure for paper 1 in Cambridge A-level physics. Now, I've taken these questions from the Papa Cambridge website where they have topical questions from past papers on all different topics, and you can use these questions to reinforce the ideas and the concepts as you are studying topic by topic. And in this video, we're going to look at questions 377 to 391 specifically. And the topic of forces, density, and pressure can be fairly complicated, can become fairly complicated, but as long as you understand the basics, like with everything I always say, you will be fine. Now, the first question is 377. It comes from the summer 2017 exam. It's question paper 1, variant 2, and it's question 10 from that paper. We are told that a metal cylinder is suspended vertically in equilibrium by a cord. The diagram shows the cylinder in 4 different positions, P, Q, R, and S. And we want to know which statement explains the variation of the tension in the cord T. Now, at P and Q, the tension T in the cord is the same because the difference in pressure between the top and the bottom of the cylinder is the same. At Q, the tension T in the cord is less than at P because at smaller depth, the liquid pressure is smaller. At R, the tension T in the cord is less than at P because atmospheric pressure is less than water pressure. And at S, the tension T in the cord is greater than at P because atmospheric pressure at S exerts no force on the top or bottom of the cylinder. So let's first look at P and Q. And actually, we can get the solution with quite little work. So at position P, I have a tension. I'm going to draw the forces acting on the cylinder, a tension acting upward. And since the cylinder is submerged, I'm also going to have an upthrust acting upward. And remember, this upthrust is equal to rho GV. And there's a weight acting downward. The weight of the rod acts towards the center of the earth, so it's vertically downward in this case. And the difference in height between the top and the bottom of the cylinder is delta H. And if I look at the situation at Q, the cylinder is at a different height, but the difference, well, the center of mass of the cylinder is at a different height, but the difference in heights of the top and bottom surfaces of the cylinder is the same, still delta H. And there's still a tension acting upward and an upthrust acting upward, which is still rho GV, V being the volume of the cylinder, which is still the same. And so P and Q actually are equivalent. And the tensions are the same because the weight and the upthrust are the same. So all the forces are acting that are acting at point P are acting on the cylinder at point Q. And so this is why I've labeled them T and T, because tensions are the same. And why am I specifically saying the tensions are the same? Because that corresponds to option A. So option A is correct, and the reason is correct as well, because the difference in pressure between the top and the bottom of the cylinder is the same. So delta H is the same in both cases. And that's why P and Q are equivalent. And so for P, I have the difference in pressure is rho G delta H, and T plus U equals W. And for the situation at Q, I have the difference in pressure is rho G delta H. Doesn't matter that the cylinder is slightly higher in the water. The difference in the pressure between the top and the bottom surface is the same. And again, tension plus upthrust equals weight. And so this corresponds with option A. Option B says at Q, the tension T in the cord is less than at P because at smaller depth, liquid pressure is smaller. So we've already disproved that. It can't be B. C says at R, the tension in the cord is less than at P because atmospheric pressure is less than water pressure. That shouldn't be the case, especially since at R, we are halfway submerged and halfway above the surface of the water. And S, the tension in the cord is greater than at P because the atmospheric pressure at S exerts no force on the top or the bottom of the cylinder. That's immediately wrong. There is atmospheric pressure on the cylinder at S. So we are left with option A. And so you don't have to redraw the diagrams like I have, but you have to understand hydrostatic pressure for this question. And so the option there, the correct option is A. Question 378 is from the summer 2017 exam. Summer is May, June 2017. Question paper 1, variant 3, and it's question 12 from that paper. We are told that an air bubble is rising through a liquid at constant speed. The forces on it are the upthrust U, the viscous drag D, and its weight W. And we want to know which of the diagrams shows correctly the directions and relative sizes of the forces. Now, the first thing we need to focus on or hone in on is the fact that the air bubble is moving at constant speed. So there's a constant velocity. It's moving just upward at constant speed. And so if we have constant velocity, what this means is that all the forces acting upward must balance all the forces acting downward. And this means now, since we're moving upward, the upthrust obviously always acts upward, but the drag is going to act downward, just like the weight. So the upthrust must equal the weight downward and the drag downward. The drag is always going to oppose the motion. It's a resistive force. And so what I need to have is an air bubble. Now an air bubble is going to have a very small weight, W. It's full of air. It's not a metal sphere or something like that. The drag is going to act downward, and the drag and the weight added together must add to the upthrust. So the lengths of the arrows pointing downward must add up to the length of the arrow pointing upward. The weight must be less than D, and W plus D must equal to U. Using your rulers, you can see which this corresponds with. This corresponds with option A. Small weight, relatively high drag, add those two together, you get the same magnitude as the upward pointing arrow for the upthrust, and that corresponds to option A. And so your correct answer here would be A. So remember, when forces are balanced, then an object will move at constant speed, and that can tell us the sizes of the arrows for the forces if we draw a free body diagram for the object. The next question is 379. It's from the winter 2017 exam. That's October, November 2017. It's question paper 1, variant 1, and question 8 from that paper. We're told that the three forces acting on a hot air balloon that is moving vertically are its weight, the force due to air resistance, and the upthrust force. The hot air balloon descends vertically at a constant speed, and the force of air resistance on the balloon is F. Which weight of material must be released from the balloon so that it ascends vertically at the same constant speed? Okay, so a little bit of a tricky one. So let's see what's happening to the balloon when it's descending. And let's try and put a picture to what's happening. So I have this balloon, and they tell me that when descending, there is a drag force or an air resistance, which we will call F. The air resistance F. If it's descending, the air resistance will act upwards. F acts upward. There's also an upthrust. That upthrust will be U. And then a weight, the weight of the balloon will act downward, W. And the sum of the two upward arrows must equal the sum of the downward arrow. And that's because the balloon's moving at constant speed. I'm going to call this weight W1. W1 is equal to the upthrust U plus the air resistance F. But now let's look at the case when the balloon is ascending. So it has a different weight because we've released some of the material from the balloon, so it has a different mass and hence a different weight. That's why I labeled the initial weight W1. But now it's moving upward. And if it's moving upward, the upthrust is still pointing upward. And now the air resistance will act downward since the balloon's moving upward. And the weight will be slightly less, it'll be W2. And what I have here is W2 plus F is equal to U. Now, this means that W2 is equal to U minus F. Now, what I'm doing here is I'm assuming that the drag force, or the air resistance rather, is constant. And I'm assuming that F is the same because the balloon is moving at constant velocity. So whether the balloon is moving up or moving down, if I can assume that the balloon has a uniform shape, then the air resistance will be the same if it's moving at constant speed up and constant speed down, and the speed is the same constant speed. So let me label my two equations 1 and 2. But you can see I have two equations for the weight. Now the difference in weight is what I want, how much of weight has been lost. So I'm going to say W1 minus W2. And I take basically equation 1 and I subtract equation 2. The u's cancel. What I'm left with is F minus minus F, which is 2F. So the difference in weight for the balloon to ascend is 2F. And that corresponds to option B. So it must lose 2F of its weight in order to, instead of descend, to start to ascend. So whether it means throwing some sandbags off the edge or whatever it may be, but the weight needs to change by 2F so that the balloon can now ascend at a constant speed, which is the same speed as the descent speed. Okay, so quite a conceptual question there. The next one is question 380, which is from the winter 2017 exam. It's from question paper 1, variant 1, and it's question 12 from the paper. We have a block that is submerged vertically in a liquid. The four diagrams show to scale the forces exerted by the liquid on the block, and we want to know which diagram correctly shows a possible situation when we view the block from the side. So let's first think about the vertical forces that are acting on this block. And we'll do the vertical and horizontal separately and then try and match the diagrams. So the vertical forces on this block, when submerged in a liquid, we know that this block submerged in a liquid is going to have a higher pressure lower down and a lower pressure at a higher point. And the resultant of this is an upthrust upward. So the arrows at the bottom are greater than the arrows at the top. The force at the bottom is greater than the force at the top, and so the upthrust means the block will be pushed upward. But the horizontal forces, what do they look like? Now remember, the forces are due to the pressure of the water, and the pressure changes with the depth. So since there's a greater pressure lower down, there's a greater force, since the surface area will be the same. Now the horizontal forces, now the pressure at the same height as we had labeled the vertical forces will be the same. So the arrow closest to the top, the pressure is the same on all sides of the cylinder, meaning the force is the same at all sides. And so that arrow that is pointing downward is the same magnitude as that arrow pointing to the right. And as we go further down, the forces, the inward pressure that causes the forces is larger, and so the inward forces are larger. And the size of the arrows at the bottom, since they are acting at the same point, is the same as the size of the arrows pointing inward horizontally. And so what this means is the arrows get bigger as we go further down, and they point upward for vertical forces and inward for horizontal forces. And so that must correspond to option A. It's the only one in the four where the arrows are the same size at the same point. As you can see in C, they sort of have the same shape, but the sizes are not the same. So we can't accept option C. Question 381 is from the winter 2017 exam. It's from question paper 1, variant 2, and it's question 11 from that paper. So we are shown a diagram of a block of copper that is suspended in water, and the block experiences an upthrust from the water, and we want to know which statement is the basis of an explanation for this upthrust. So what explains the fact that there is an upthrust? Not so much the size of the upthrust, but the fact that there is an upthrust. So if I were to draw this block from side on, longer at the bottom, shorter at the top, there is an upthrust U. But remember where the upthrust comes from. The upthrust comes from the fact that the top surface and the bottom surface are at different heights. So H1 and H2 are not the same. So the difference in pressure is rho g delta h, and therefore there is an upthrust. There's a U that exists. If I were to change the shape of this object and make it into a cylinder, and I look from side on, the top and bottom surface of the cylinder were the same in size, they would still be at different heights, at different depths below the top surface of the water, and so there'll still be an upthrust. So can I say that it is because copper is more dense, or because face S has a larger surface area than face R? No, because there's still a delta P, there's still a rho G delta H, and there's still an upthrust. So again, there is a U that exists, there's an upthrust that exists. And so the origin of this upthrust is because the pressure increases with the depth. And so the very fact that we have two surfaces, one at a greater depth than the other, there'll be an upthrust, and this corresponds with option D. So remember, if you know your definition of upthrust, then this wouldn't really be a difficult problem. The next question is 382. It's from the winter 2017 exam, question paper 1, variant 3, and it's question 11 from the paper. A stone is projected horizontally in a vacuum and moves along the path shown. X is a point in this path. XV and XH are vertical and horizontal lines, respectively, through X. XT is the tangent to the path at X, and we want to know along which directions do forces act on the stone at X. So a lot of directions and geometry here, trying to throw you off. But it's not going to throw you off because you know your forces very well. So what's happening to the stone at position X? Well, here's my stone. Here's the forces acting on the stone. There's only one force. It's only the weight. There is no horizontal force. It's in a vacuum. There's no air resistance. So the only force is the weight, and the only force is along XV, along the line XV. Remember, XV is just a line. And so that corresponds to B. Maybe trying to catch you out with a little bit of wordiness and verbosity, but again, we know that there's only one force acting on the stone. That's the weight acting vertically downward. Nothing else is acting on this projectile. We usually ignore air resistance for projectile motion anyway. Question 383 is from the summer 2016 exam. It's from question paper 1, variant 3, and it's question 13 in that paper. We want to know what is the center of gravity of an object. Is it the geometrical center of the object, the point at which the weight of the object may be considered to act, the point in the object about which there is zero net torque, or the point where gravity acts on the object? Now, it's difficult to say the point where gravity acts on the object because gravity is more of a concept than a measurable thing, than a quantity. But it doesn't really matter, because if you go to the definition, if I asked you to open your textbook and find the definition of center of gravity, what would you find? Again, this is testing how well you know the definition. It is the point at which we can consider weight to act for an object. So I'm going to be lazily say it's the point at which weight acts. Weight is a vector. The vector acts at this point, and this is by definition. So you're not going to get this one wrong. And this corresponds with option B, point at which weight of the object may be considered to act. Or at least you shouldn't get this one wrong. The next question is 384. It's from the winter 2016 exam. It's question paper 1, variant 2, and it's question 14 from that paper. We are shown 4 diagrams, and we want to know which of the diagrams best show the forces acting on a ball that is falling at constant velocity through a liquid. So again, what do we remember from constant velocity? It means all the forces are balanced. And this is a ball in this case, and not an air bubble like we had in a previous question. So that if the velocity is constant, the weight must equal the upthrust plus the drag. Because it's falling, the drag will act upward. It's moving downward. And so here's my ball, has some significant weight W pointing downward. And then there must be an upthrust and a drag. And the sum of those arrows must equal the length of the arrow pointing downward. And this, as we can see, if we would just use a ruler, we could see that corresponds to option D. Upthrust plus viscous drag both act upward. Upthrust by name always acts upward, but drag is upward because the ball is falling down. Since it's constant speed, the weight must equal the upward forces. And so that's option D. Okay, so we had a good break with some relatively straightforward questions. The next one is also relatively straightforward. We're told that an astronaut, this question is from the summer 2015 exam, question paper 1, variant 2, and it's question 12 from that paper. An astronaut throws a stone with a horizontal velocity near to the moon's surface. Which row describes the horizontal and vertical forces acting on the stone after release? Okay, the last time I checked, the moon has no atmosphere, no air resistance, so I throw a stone horizontally with some speed u. It then moves a lot further before it actually starts to slowly fall towards the ground. And if I trace this motion out, at any point in this motion, after the release, there is no horizontal force acting on the stone, no air resistance, nothing at all horizontally. There will be a force due to the moon's gravity. We'll call it Fg. And that will be the only vertical force acting on the stone, just like it would be on Earth. It would be not the weight as we would imagine it on Earth. It would be a slightly smaller value, but it's still a force. And since the moon's gravitational field close to the surface will be constant, this value will also be constant. And so horizontal force would be 0, so the answer can only be C or D. Vertical force must be constant, and so this corresponds to option C. Okay, so again, it would be exactly the same case if we were thinking of the Earth. Actually, there wouldn't be a horizontal force unless we were considering air resistance. Now we're moving on to the turning effects of forces. The next question is 386. It comes from the March 2020 exam, question paper 1, variant 2, and it's question 12 from that paper. We are told that a uniform rod of weight 20 newtons and length 2 meters is acted upon by 2 vertical forces as shown. What are the resultant force acting on the rod and the resultant moment about the center of gravity of the rod? Okay, so here's a nice question. Well, I guess it depends on how you define nice, but a little bit more challenging than the previous questions that we were working with. We like challenging questions. The rod is uniform and it has a weight, which means the weight acts through the central point. The center of mass is where the weight acts, and that's 20 newtons vertically downward. And on either end of this rod, I have an upward force. On the left-hand side, it's 15 newtons. On the right-hand side, it's 5 newtons. And the rod is 2 meters in length. So the distance from the point of contact, or the point of application of the force, to the central point is a meter for each of these forces, because the total length of the rod is 2 meters. And so let's find the resultant force, shall we? The net force is equal to the upward forces, 15 newtons plus 5 newtons minus 20 newtons in the opposite direction. The net force on this rod is 0. There is no net force up or down because the upward forces balance the downward force. What about the net torque? I'm going to use the Greek letter tau for torque. And this is equal to, let's look at the turning effect of the 15 Newton force. So that's 15 newtons times 1 meter, since the perpendicular distance of that force is a meter to the central, to the center of gravity of this rod, which is the central point. Now minus the 5 Newton force, also acting at a meter perpendicularly for the rod, And that's because the first force, the 15 Newton force, will cause the rod to rotate clockwise about the center, but the 5 Newton force will cause the rod to rotate anti-clockwise about the center. And so we have to have opposite signs for clockwise and anti-clockwise moments. And so we get a net torque of 10 Newton meters. So net force of 0, net torque of 10 Newton meters, a net moment of 10 Newton meters, and this corresponds with option A. So we need to know how to calculate net forces, but we also need to know how to calculate net torques as well, net moments. Question 387 is from the summer 2020 exam. It's from question paper 1, variant 1, and it's question 12 from that paper. We're asked which statement best describes a couple. Well, this again will not be difficult because you should know what the definition of a couple is, but I'll refresh your memory. Here's a rod simplest example, and a couple is a pair of forces, hence the name couple, acting on two opposite ends of this rod. I'll call one F1 and the other F2. They need to be in opposite directions and they need to be equal in magnitude. F1 equal to F2. And the result of this means that the net force on this rod is 0. So this rod will neither translate up, nor translate down, nor translate left, nor translate right. But it will rotate because the net torque will not be 0. Because I have an anti-clockwise torque and another anti-clockwise torque. And so obviously two anti-clockwise torques can't balance, and this rod will rotate anti-clockwise. If there's going to be a rotation, there has to be a net torque. And this corresponds to option A. Pair of forces of equal magnitude, check. Acting in opposite directions, check. Which produce rotational motion but not translational motion, check. So that's a statement that describes a couple. And if you know the definition for a couple, you wouldn't have to draw a diagram and try to convince yourself like I did. If it helps, by all means do it. The next question is 388. It's from the summer 2020 exam. Question paper 1, variant 1, and it's question 13 from that paper. We're told that a uniform rod XY of weight 10 newtons is freely hinged to a wall at X. It is held horizontal by a force F acting from Y at an angle of 30 degrees to the horizontal as shown, and we want to find the value of F. Okay, so a little bit of a complicated question, but this is a good application of moments. And I'm just going to redraw the diagram. I have a hinge here holding this rod, which luckily for us is uniform, holding it horizontal. But there's also a force acting up and to the left, F, that is helping hold this rod in place. And that force acts at an angle of 30 degrees. The weight of the rod will act through its center of gravity downward, and that's 10 newtons. And we have 2 points X and Y, either end of the rod. And what I can then do is I can label my vertical component of the force F. I'm going to call it Fy. And your math skills will tell you that this is F sine 30 degrees. And I'm going to call the length of this rod L, just for simplicity's sake. We'll see why I need that. Now I'm going to take moments about X. Now the reason why I'm not going to use the balancing of forces is because I don't know what the force that X applies at the hinge. I don't know what force is being applied at point X, rather, on the rod at the hinge. So the hinge is applying a force onto the rod, but I don't know what that force is. So I'd rather take moments, and I'm going to use X as the pivot point. So whenever you choose a point to be a pivot point, you immediately remove it from your calculations. So I'm going to take moments about X, and I'm going to take clockwise moments and anti-clockwise. So my clockwise moment is going to be the weight acting downward, and the weight acts at a distance of half of the total length of the rod because it's acting through the central point. And the anti-clockwise moment is going to be the Y component of F, since we are looking at the perpendicular component of the perpendicular force compared to the rod. which is Fy, and it acts at a distance of L, acts at the opposite end of the rod. So now you can see the L cancels, and I don't really need the length to find the forces. And so F sine 30 degrees, I'm going to bring F on the left-hand side, is equal to a half of the weight of the rod. And so this force F is equal to 10 newtons, which is the weight of the rod, divided by 2 sine 30 degrees, which gives me 10 newtons. And this corresponds with option C. So you can see I needed to use moments and not forces. And that was kind of what the question was getting me to do. If I used forces, I would get stuck. But if I used moments, I can see that the lengths cancel on either side when I'm calculating the anti-clockwise and clockwise moments. And so I can solve for the value of F. And F here is 10 newtons, not Fy. So the actual value of the force F is 10 newtons. And when you see a problem like this, I think usually the question is trying to lure you on to using conservation of moments for an object that's not rotating. So balancing of moments when an object's not rotating, when you see something hinging and has a weight pulling it down and some force pulling it up. So this is a common type of problem on the topic of moments of force. Now the next question is 389. It comes from the summer 2020 exam. It's question paper 1, variant 2, and it's question 11 from that paper. So quite an interesting one. We are shown a bicycle pedal connected to a pivot by a metal bar. The force on the pedal is 60 newtons downward. We want to know the moment of this force about the pivot. So how much of that force we're applying, 60 newtons is quite a significant force. How much of that force is actually going to be turned into a turning effect? So it's a little bit of geometry, as you can see. I'm going to redraw this, the pivot point, the bar, and the pedal right at the top. And there's a force acting vertically downward, F. But what we're really concerned about is the component of this force that is perpendicular to the bar. Remember, we always want the perpendicular components of forces. And you can do the geometry if you want to convince yourself. If that angle is theta, then so too is that angle. That angle is also theta between F and F perpendicular. That side has a length of 20 centimeters. And the bottom side has a length of 16 centimeters. Why am I doing this? Because if I use some geometry, I can find the angle theta. So the angle theta, and if you know me, I prefer to do the algebra first and arithmetic later on, but let's find the angle theta. It's the arc cosine of 16 over 20. Okay, so we're using that right angle triangle and some trigonometry, and we find that the angle theta is 36.9 degrees. So now that I have the angle theta, great, how do I find the moment of the force? Now the moment of the force, there's going to be a component parallel to the bar, which is along the bar. That's obviously not going to make the bar rotate. But the component of the force that is perpendicular to the bar, what I've labeled as F perpendicular, that's going to cause the moment. And so this moment is equal to the perpendicular component of the force times the distance to the pivot along the bar, which is 0.2 meters, 20 centimeters. And there are a lot of lengths here, so it's easy to get confused. But remember, we're looking at the distance along the bar from the point of application of the force to the pivot. And so F perpendicular is F. Actually, let's figure out what F perpendicular is going to be. If I do it aside here, here's F coming downward, and I broke it up into F perpendicular to the bar, and then F parallel to the bar, along the bar. The angle between F and F perpendicular we said was theta. The angle between the two components must be 90 degrees. We can break up any vector into perpendicular components. And so with a little mathemagic, we have that F perpendicular is F cosine theta, which means this is 60 cosine 36.9 degrees multiplied by 0.2. So the moment or the turning effect of this force is 9.6 Newton meters. And this corresponds with option B. So an interesting question, also one that this forms the basis of moments. If you don't understand a question like this, then it's probably safe to say that you don't really understand moments. So my suggestion would be to make sure you understand how to do this kind of question day in and day out, because this will be a common recurring type of problem that you're more than likely to see in either paper 1 or paper 2 always. The next question is 390. It's from summer 2020. It's from question paper 1 variant 3, and it's question 12 from the paper. We're told that two forces, each of magnitude F, act along the edges of a rectangular metal plate as shown. The plate has length A and width B, and we want to know the torque about point P. Okay, so we first have to consider, let's redraw this in fact. Let's draw the point P, and then draw the line joining the points of application of the forces. I have one force pointing to the right, F, and one force, actually, we can see that point P is closer to the bottom, so it's not symmetrical like we normally have our picture showing us. So point P is closer to the force at the bottom than it is to the top. Now both these forces are equal in magnitude, opposite in direction. We want to know the torque about point P. Now the torque is going to be perpendicular to the forces, so it's going to be along the line joining the point of application of the two forces. And if the entire length is B, then I'll call the length from the upper force to P X, and the force between P and the distance between the point P and the lower force, I'll call it B minus X. So they want to know the torque about point P. So the net torque, I'll call it tau again, is, and both of these are going to cause a clockwise torque about point P. If I look at the upper force, it's going to be F times X, if point P is our pivot point, plus also a clockwise torque caused by the lower force, which is F times B minus X, because that's the distance that F at the bottom acts. And you'll notice something happens. I get F into X plus B minus X, so I bring out F as a common factor, and guess what? I get the torque simply to be the force F times the separation of the forces, which is the force of a couple anyway. So along any point, so on any point along the line joining the two forces, the torque will be the same, FB, which is option B. So another interesting question to try and just challenge the underlying understanding of the concept of torques. The last question for this video is 391. It's from the March 2019 exam, from question paper 1 variant 2, and it's question 12 from that paper. A fairground ride consists of 4 carriages connected to a central vertical pole as shown in the following view from above. A motor rotates the central pole about its axis. This results in the 4 carriages each moving along a circular path. The distance from the middle of each carriage to the center of the pole is 3.2 meters. When they are moving, each carriage experiences an air resistance force of 85 newtons. Assume that there are no other significant resistive forces. Which torque does the motor need to apply to the pole to keep the system rotating at constant maximum speed? So 2 ways of answering this. One would be the way that I'm going to show you. The other would be to leave this question and just carry on with your life as if you've never seen it. We'll go with the first option for this one. Let's just redraw these rods because this question seems like it might be a bit confusing. So I have a rod, I have a central point, I have a lower rod. These 2 rods are vertical, and there's going to be an air resistance which the motor has to overcome. So we'll call the force which balances the air resistance FR, and it's 85 newtons. And on the lower arm, guess what? There's another FR, also 85 newtons. But we also have two more rods. The horizontal rods, they are also the same length, and the motor must provide a force to overcome the air resistance Fr downward on the rod to the right and upward to the rod on the left, because the entire system is rotating clockwise. And the distance between the forces on either end of the arms is 6.4 meters. So actually these are two couples, 6.4 meters and 6.4 meters. So these are actually two couples that we are seeing. So the total torque that needs to be applied to the engine is equal to the vertical couple. So the couple applied on the vertical beams plus the couple applied on the horizontal beams. Aha. So we have two couples, hence the torque is the sum of the two couples. And these two are symmetrical. So that's 85 times 6.4 meters. That's how we calculate a couple. It's the force of one times the distance that separates them, the perpendicular distance that separates them, plus the horizontal couple, also 85 times the separation of 6.4 meters. And so the total torque that needs to be provided by the motor to keep them moving at a constant speed would be 1090 Newton meters. And this corresponds with option D. So this question was very wordy, but if you think about what is actually happening here, you essentially only can consider this to be a problem of two couples, or four moments if you would like, and four additional moments, but that would be the moment of the force on each edge of each of these four arms, but you'd end up with the same answer. And so if you see something like this, just simply break it down into the basic concepts that you understand for moments of a force and for the torque of a couple. And this was the last question for this video rather. And I hope these questions were helpful. I hope you're using these questions to help you prepare for paper one, because paper one can be, as you've seen, quite tricky and not as straightforward as it may seem because it's multiple choice. So if you found these questions helpful, please leave a like, comment on the video, subscribe to the channel if you haven't already. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.